People see the screen?
Yes.
Perfect. So let me get started then. So good afternoon, everyone. And today I'm going to talk about observation operators and quality control inside of JEDI. So just a bit of background, or to start, one of the big goals of JEDI is to enable scientists and engineers to rapidly extend data assimilation to new missions. So we want to redirect work from being more focused on repeating common software engineering tasks in favor of having enough time to do more science. And we want to build reusable components for operators and quality control and bias correction that different groups can customize to fit their needs. And we want to do this ideally without having to change the source code of JEDI too much. And this idea where we can configure our workflow is the essence of having generic and customizable unified forward operators and generic quality control. So this presentation is going to walk you through the basics of how UFO actually works. And much of what I am talking about is implemented inside of the UFO repository, but a lot of the interfaces are located within OOPS. And Anna talked about that a little bit earlier in some of the talks, and so did Yannick. And this split between interface and implementation is a really central concept inside of JEDI, although it means that in order to understand these features, you do sort of have to glance back and forth between either two repositories or perhaps two tabs of a browser window or two source code files to really get the benefit. For the first half of this talk, I'm going to introduce some of the core classes inside of UFO, which are shown on the left here, starting with GeoVals and continuing onwards through QC. Now, tomorrow we have planned a practical exercise that's meant to introduce you to writing a new generic QC code to filter some data. And that should be the first exposure that you all have to modifying the JEDI source code. So to keep on time, I'm not going to discuss bias correction, although it is heavily related to some of the concepts discussed here. So I'm going to give some examples in the context of satellite radiance calculations. And UFO is not by any means restricted to this, but it is a good example. And say that you have a model and you want to figure out what an orbiting radiometer will see at certain locations. And say that this is a forward type of modeling problem. And let's also assume that these locations don't coincide perfectly with the grid of some model that you have. Now, this can be a bit of a hard problem, but I'll try and break it down into a few steps for you. So for radiative transfer, let's say that the model already provides a couple of variables that are useful, like surface emissivity and column-wise or vertical profiles of temperature, of water vapor, of ice water, grapple, and so on at a set of fixed locations on a grid. So what you would first want to do in the forward problem is interpolate the data on your model grid to match the locations in space and in time where you're taking your observations. And this is accomplished by the GeoVals code, which stands for geophysical values at locations. Once you've done this interpolation, then you can actually apply an observation operator. For radiances, this is usually the community radiative transfer model, and we can convert the model state variables into a set of observable variables like radiances or brightness temperatures. And since no algorithm or sensor is perfect, we also can apply a bias correction transformation to attain better agreement with what the simulated observations would be. And then also at each of these steps, particularly around the operators, we can also set and record some quality control information, or maybe adjust error estimates. Now that is a lot to absorb, so I'll break it down even further and explain each of these components piece by piece. So this should give you an idea of how UFO works when you actually want to run. And let's start with the interpolation. So GeoVals again stands for geophysical values at locations, and it's used to pass the model variables interpolated to the required locations that you want off to the operator. So it basically acts as glue between the model and your desired observables. So you use GeoVals to do this type of horizontal and temporal interpolation, and we split this implementation into two parts. So we've got the model or grid aware part, which actually does the interpolation, but it's done in the context of the model. So along certain grids, like the grids used in FE3, there are very efficient algorithms for interpolating your data, but you might also have a model closer to, say, MPass, where it's a lot harder to do this. So on that side of GeoVals, it's model aware or model specific. But on the other side, we want to make sure that all of our observation operators, and I'll discuss those in a little bit, can access all of the data through a very uniform interface. So that's the model agnostic part. So GeoVals provides a couple of functions that an operator can call, and the operator can get all of its data without having to know the model specific details. So it's also important to emphasize that GeoVals in this case represents interpolated vertical profiles at a location. And also GeoVals can vary. We can have more than one GeoVals class. So in the case of having a satellite footprint where a satellite can see several different model locations at once, just say like a radiometer looking down, then GeoVals also does a little bit of mixing of the data or convolution. And also, we don't interpolate every variable that the model provides either, because that would be inefficient. We're only actually interpolating and extracting the data that the operator needs to function. And we only, again, interpolate over those. So for example, again, with satellites, we need all those vertical profiles of all those different variables, and we need some surface information too. But often, say, a trivial case where we're just trying to extract sea surface temperature from a model, and the model already provides that, we just extract it. We just do the interpolation there without caring about anything else. So now once we've done this type of interpolation, or once we have the GeoVals, then we actually want to calculate our observables using our observation operators. So in the context of that microwave instrument example earlier, we would want to simulate brightness temperatures using the community radiative transfer model. And conveniently, we've already implemented this model and quite a few others as generic operators that you can access. So from the configuration talk earlier today, you saw a bit of YAML, and each observation operator is generic in that it can take a set of options inside of YAML, so it's customizable. So for example, look at the left column on this slide, and this configuration block states that we want to call CRTM, and that we also want to turn on things like gaseous absorption by water vapor, ozone, and carbon dioxide, and that we want to assume that the retrieval can have both liquid water and ice clouds. Now, if you don't want one of these features, you can comment it out and disable it. Although with CRTM, you have to keep 2 of those 3 absorbers, but that's errata. But the big takeaway is that there's no need to write new C++ code. For GNSSRO calculations for bending angle, it can take its own set of options. Same with vertical interpolation. These slides, by the way, are clickable if you've downloaded them, so you might see the links 1, 2, and 3 on the text, and that will take you to a YAML example showing how this operator is used in context of the rest of the actual run. So setting up of what's called an observation space and doing also the QC. So now that you've seen the YAML side, I'll just very briefly touch on what the obs operator object looks like in C++. So every operator in UFO inherits from this base class. And for those who don't know what that means in C++ terms, that means that all of the operators have the same general interface, but they specialize a couple of key functions that always will have the same signature. Or basically, these functions all look about the same. So those are all denoted with that virtual text that you can see on the slide. So every operator has a simulate obs function, which actually runs the operator. Every operator also returns the list of variables that it requires to do its job, and so on. Now, if you want to think a bit more visually or with a diagram, here's a bit of a schematic to show how this all sort of works. So you, the user, are specifying that you want a specific operator to produce specific simulations of observables. Or maybe you want to go in the reverse direction and do some data assimilation. So the operator needs to ask the model for data at specific locations. So it calls geovals to handle this. Geovals talks to the model, does the interpolation, and returns the data to the operator. It only does it for certain variables that the operator needs. And then once the operator has what it needs, then it can actually execute its operation. So again, JEDI provides quite a few operators, and they span calls to radiative transfer models like CRTM and RTTOV, to GNSSRO related computations, to other types of interpolation, say in the vertical domain. And also we have some marine DA operators. We've got quite a few. And one other key thing is that if you click on these links, you're going to be exposed to, again, C++ files. So I've mentioned also that you can call these through YAML, and this is a really key concept in that we haven't hard-coded the application logic anywhere. So UFO is entirely generic, but we do need some way of translating user instructions into the appropriate operations. So if you ever browse UFO, you'll see that we've implemented what's called an object factory pattern to do this. And of course, you might wonder what I mean when I say an object factory. And this factory class is a type of like repeated pattern in programming that's used to make individual objects. And an object is a set of data and functions that operate on that data that are all just encapsulated together. So we could have a whole bunch of possible operators that we could create, and we don't know at compilation time which ones we want to use. So what we do is in C++, we ensure that all those operators inherit from that common base class called obs operator base. And then our actual programs call this function called create in the factory. And we feed in a YODA obs space, which is our input data. And then we also feed in a block of code called an ECKit configuration object, which represents YAML in a C++ readable form. So it provides functions where we can just say, does the YAML have a certain key, list all the keys, iterate over them, and extract the names of the operators. And that's how we handle that mapping. So this factory translates what the user provides into the construction of the operator itself. Now, we apply the same pattern for both observation operators and also for QC filters, bias correction, and in a whole bunch of other places inside of JEDI. So again, it's worth mentioning because it pops up in at least 15 different situations. So again, here's what this looks like in YAML. So that key that I mentioned with ECKit is the operator name. So when we get past an ECKit configuration, there's a block called obs operator, and then we have the name of the operator and its settings, and that just gets read by the YAML parser, and then it gets passed to constructor objects. All these operators register themselves inside of the code using this static obs operator maker function. And then basically they're available whenever you want to first create a new operation. So we have obs operators, and I've mentioned obs operator base in the factories, but we also have a couple of related objects that exist inside of UFO also. So we also have linear obs operators. And linearization is important for things like cost function minimization and data assimilation. So basically, you can do a retrieval based off of a set of measurements and go in the inverse direction and try and assimilate what your actual state is given your observations. So the linear operators are implemented really similarly to regular operators. And they're configured in YAML, and they're also created in runtime using a factory class. So here's what the interface looks like in C++. And I won't show this for too long, and you can reference it at your convenience, but there are two sort of takeaways. And the first is that compared to a regular OBS operator, we've got some extra functions, and those are highlighted in red here. And then also our OBS operator and our linear operator can act on different variables that are available inside of our data. So for the first set of those, in a linear OBS operator, we have methods that implement trajectories and calculate the tangent, linear, and adjoints of our observables. And basically that means that we can calculate Jacobians and we can perform work on increments. So we have three functions here. So set trajectory to calculate the Jacobian. We've got simulate the tangent linear OBS, and then we also have simulate OBS adjoint. The other takeaway here is that we can also differentiate on different variables than we otherwise would use in our regular OBS operator calculations. So we have like some examples here. So for a vertical interpolation, a regular OBS operator requests that the model provide air temperature and air pressure in order to do its work. But when we're trying to do the tangent, linear, and adjoint calculations, the linear operator is only updating air temperature because we don't care about updating pressure. Another example is for CRTM. The OBS operator itself requests a lot of information about the surface, or like the Earth's surface. And not all of that are representable by continuous variables. So for example, in some of the ways that you can call CRTM, you can assume that, that there are a couple of different types of ground. Say, for example, you can have open ocean, or you can have snow-covered grass, or you can have desert. And these are categorical variables. They're not continuous. So the linear OBS operator doesn't really update any of these, and these are left to be handled outside of the main retrieval loop. So that was a lot about observation operators, but UFO also has one other big side to it, and that's the observation filters. So this is how we handle quality control inside of JEDI. And these filters, just like with the OBS operators, are written to be very generic. So again, that means that these filters don't depend on specific observation types and are configured through YAML. So these filters execute either before or after the operator. So you might have situations where you want to filter out data before you try and run an operator on it. Say, for example, when you have bad data that's obviously bad. Or you might want to execute afterwards and say, okay, something looks like it didn't retrieve properly or it didn't get simulated properly, so let's filter it out there too. And this customizability lets the UFO encompass a lot of the pre and post-processing work that's performed in existing codes running in operational centers. So these filters can change quality control flags. So again, they can reject or retain observations, and they can also modify observation error variances. So you might wish, for example, to increase the error variance to decrease the observation weight in an analysis instead of just altogether rejecting an observation. These filters also have direct access to a lot of the data that's available to YODA and OOPS, so they're very powerful. So we have increasing numbers of filters that are available to UFO, and this is an area in JEDI where we're regularly trying to develop new techniques that we can distribute among end users. So for some of the traditional ones, we can of course filter based off of upstream flags. That's called pre-QC, where some upstream data source has already flagged its observations and we can just import it into JEDI. We can also do things like restrict the domain, the spatial or temporal domain of our observations, or we can filter based off of variable values and so on. We also have generic filters to compare two variables to each other and look at their relative errors and reject observations that are too far apart. We can do this with unrelated variables, or we can even do this for observations compared to our background. And then we can also easily extend these filters using what's called the OBS function interface in case we have some very complicated QC that we can't make or produce as a composition of a lot of simpler operations. And I won't get into that too much here, but it lets us, again, do very complicated logic decisions. So all of the filters are well documented and they're available in our Read the Doc site, just like the OBS operators. So if you do want the full list, just click on the link on the slide. But let's just go through a few filter examples during the rest of our time to see how you would actually implement these. So the first is really simple, and this is the bounds check filter. And it does what it says. It filters out of range data. So this is just a YAML snippet taken from the Read the Docs documentation again. So you specify the filter by its name, so bounds check, and then you say what you're applying it to. So in this case, you want to filter out the brightness temperature observed by that's recorded by some instrument. So again, like with the radiometer, you can have multiple channels which represent ranges of frequencies that the detector is sensitive to. So in this case, we want to filter out our data based on channels 4, 5, and 6. And then we can QC flag the data where the brightness temperature that we measure is less than 240 Kelvin or above 300 Kelvin for those channels. So obviously a case where, say, the Earth's surface is way too cold or way too hot. Now we can go to something a bit more complicated, and I can show off some more features of filters, and we can look at the domain check filter too. So this in practice is, or in concept, is very simple. So a domain check accepts only data that fits within a where clause. So this is one of the features of our filters too. We can restrict a filter to operate only on a specified subdomain, basically specified in where. And when we have multiple criteria that we all group together under that where statement, all of those where clauses go through an and operation, or basically the net result is the intersection of all of the different statements that you specified. So in this case, we want to do sanity checks on some of our data that's going into a system. And we want to do sanity checks probably on buoy data. And we want to look at the sea surface temperatures, the height, the station IDs, and the air pressure. So in this case, for the where, we can say where the sea surface temperature is at least 200 Kelvin and not greater than 300 Kelvin. If you're out of that range, throw it out. We can also filter out on height. So in this case, the context of height depends on what it means in the upstream observations, but we only want to retain observations where this quantity is defined and not set to a missing value flag. We can also have what's called an is-in statement. So we can filter based off of station IDs and say that the station ID has to be number 3, number 6, or anywhere in the range of 11 to 120. And then lastly, to complement is defined, we want to select only observations where the air pressure is not defined. So again, that just all goes in together, and that just is part of a where block. So here's some meta C++ code to show how this is actually implemented. And we'll see something very similar in tomorrow's practical. So that's the morning practical for Wednesday. So the domain check itself isn't complicated. Most of the logic is in that process where function. So there's this vector of bools called inside. And this is basically a set of flags saying, is this particular location in the where or is it outside of it? And then after we've gone through and processed the wheres, then what we do is we iterate over all of our variables and all of our locations. And we say, if we're not inside and if we haven't flagged it already, then apply a flag saying that the domain check has failed for the set of observations. Now, here's another concept that's interesting with filters. We have this variable that we can set called flags. And in this case, we flag data that hasn't been previously flagged before. So this lets us track the flow of QC through our system. So basically, we retain the markers saying, where did the QC first fail? So when we want to go back or when we want to compare two different systems like JEDI versus NOAA's GSI, we can make sure that the QCs all executed in the same way on the same data. We actually want to expand the flags in the future a little bit so that we can say, okay, this got flagged in the YAML for this QC check as opposed to another one in case we have two domain checks, because right now they would sort of overwrite each other's values or you couldn't distinguish them. But again, future work. And for right now, it seems to be working. Okay. We have more than just very simple QC filters also. So here's an example of the track check filter, which can track either a ship track or aircraft trajectories and ensure that the observations remain consistent along a track. So in this case, you always can assume that your data are going to be very noisy, and that not only are they noisy, but you might also have some bad data inside of that noise. And this helps you try and filter it out. So you can assume that that spatiotemporal resolution of the observations is within a certain set of values, and that sets up the search. Then you can look across a set of observations and compare, say, the nearest three along the trajectory in each direction. And you can use that to set up a filter saying, okay, maybe you're climbing too fast with an aircraft observation. Maybe you should reject that. Or maybe you're moving too fast horizontally and you should reject that too. This is a statistical filter, so we actually do a test with a rejection threshold to make sure, okay, maybe a single point is bad or maybe the track itself is bad along this segment. And then for the most complicated examples, we again have these OBS functions. So here's an example from Noah from Emily Liu. And this is the QC flowchart for one routine for infrared sounders, where we're doing a whole bunch of checks and splitting our checks then based on the observations or based on the results of previous checks. And then eventually we can say, do we want to accept or reject some operation? Now, there's one more concept related to filters in UFO, and that is, again, that filters can apply different actions based on their results, and you can customize this. So by default, if you fail one of the QC checks that you've specified, the default action is to reject. So in this case, we can run a background check. So we can compare O minus B for air temperature. And if we're beyond a certain relative or absolute threshold, we can just throw out that data point. You can also do something more complicated, say inflate the observation error by a factor of 2 if you fail a certain check. You can also assign error, but that's very lengthy, so I'm not going to really show that here. But again, these are customizable objects. Anyways, now you've got a very basic exposure to the workings of UFO regarding the geovals, OBS operators, and QC, and you should have an idea of how this all fits together inside of JEDI. And I know that this can be a bit much to take in, but it makes a lot more sense with the repetition. So we will play around with adding in a new generic function during tomorrow's practical, and this should also give you some exposure into modifying the JEDI source code. So I guess it's time to just say thank you and see if you've got any questions.